Welcome back to Industrial Problem Solving. My name is Dave Roysum. This is the last clip in the Street Smart section of this course. No worries, we still have many more tools and techniques to cover in later modules of this course, including even more Street Smart methods. One goal of testing is, almost always, laziness. Specifically, the least personal effort to figure out the essential mechanics of a problem. Sometimes it is helpful to set up a system so that it is most sensitive to changes in a knob that we are studying. More specifically, we want the defect or problem rate to be conveniently high, but not too high. The most common term for this concept is accelerated testing. In electronics, for example, test technicians may apply simultaneous vibration and heat well beyond rating to intentionally increase the failure rate. This is not quite the same thing as the exaggeration tool we discussed earlier. We aren't exaggerating the knob we are studying, rather a different one, so that the failure rates are convenient to study. If the rate is too low, trial durations are tediously or impractically long. An example here from web handling is web breaks per roll on a newspaper printing press. Breaks are typically a couple of percent. With defect rates of 1 per 100 rolls, trial sizes may need to be as high as 1,000 rolls to be statistically solid. If, on the other hand, the rate is too high, we could get buried in trouble. Continuing with the web break problem, a break rate of 100 per roll instead of 1 per 100 rolls would not be practical to study. Even 10 breaks per roll would be too high, as the system would never really achieve a steady equilibrium. One way to adjust web break rates is to increase tension. Then the difference between suppliers, or a before and after roller alignment comparison, or any other operational maintenance change might be seen in a few rolls instead of a few hundred rolls. Let me give you another example I worked on that uses similar ideas. The problem we were studying was which spreader worked best on a very wrinkle-prone film. People who have taken my Web 101 course, which is now 5,000, would know that there may be at least a half a dozen decent spreader candidates for thin film. So while the literature is clear what options we have and how best to set them up, it is not at all clear which option is best for any particular situation. Only the real world of your specific system can give you that answer. The setup was made much faster by operators who knew that a certain tension gave the least wrinkling troubles and, of course, they ran it at that tension. If tension was increased or decreased, wrinkle rates got worse. Those of you familiar with my optimization works know that the U-shaped curve is common and is usually the result of the superposition of two different phenomena. The trouble is, for the trial anyway, that the rate of wrinkling was too low for practical study. Thus, we increased the tension for trial purposes and got the answer within minutes. It was a bent pipe instead of a concave roller or bowed roller that was clearly best. Indeed, we got the answer so quickly, we even had time remaining to optimize on the bent pipe design, such as shape, magnitude, and even construction. Sometimes you might be able to slow the machine down to reduce the amount of waste during the trial. In fact, those that have been to my Web 101 class know that not only is trial rate decreased, you might also get better answers at lower speeds, at least for wrinkling, because the system may be less forgiving and thus more sensitive. Counting the number of independent knobs and the number of independent goals is a way to check whether systems are over-constrained. Typically, the number of knobs on a process are fewer or far fewer than the number of knobs on that machine. What this can do is give you the illusion that you have more control than you really do. From our Web 101 class, I described 3 common processes in great detail and how to count the number of process knobs. While your mileage can vary, winding is typically only a 1-knob process. Science teaches us that much of winding is about tightness, and tension, nip, torque, and speed, known as the TNTs of winding, all change tightness. In that way, there is no difference in tightness produced by tension or nip. It is just tightness. If you knew that, you can much simplify your winder troubleshooting. Similarly, calendaring is typically a 1-knob process, while laminating curl is a 2 to 5-knob process, depending on whether you can change materials or have certain somewhat uncommon laminator design features. This was all well covered in my Web 101 course, so we don't have to repeat that here. So, what's the point of all of this? It is simply to recognize insolvable problems that may be handed to you. Perhaps the most extreme example here is the famous saying, "Fix it, but don't change anything." My Web 101 students know how to recognize several overconstrained systems, such as trying to fix tight and loose defects in the same row by playing with the winder TNT knobs. We also covered in great detail calendaring and laminating examples. Bounding and estimating are very useful troubleshooting skills. They are especially important in the very common case where exact answers are difficult or even practically impossible to get. Bounding means you know for sure that the answer must lie between one value and another value. Estimating means you know about how big something is. Many times these values come from lots of experience and sometimes from trials. My wife, bless her soul, sometimes has difficulty in offering specific time estimates for certain activities. At the risk of offending her, I offer the supper time calculator spreadsheet. Please pause the tape and study and see how this was done. We discussed both laziness and the shape tool in detail in previous modules. Here we are going to put them together to save measurement time and also improve the worth of the results. As an example, let us suppose that we have baggy edges, plural. We know that the shape of the problem is smile or frown shaped. We also know from lots of experience that most bagginess is the result of winding webs with a thickness profile variation. To see if our thickness measurements can pick that up, we could do evenly spaced sampling. However, a lot of the samples from the front quarter point to the middle and onto the back quarter point would be quite similar. On the other hand, you would only have a few on the edges where we are interested in studying. Instead, we could focus our efforts to put more measurements on the area of change near the edges, as with this sampling program. The distinction is that instead of finding out what the thickness profile is, we presume and check it that it is smile-shaped, and then proceed accordingly to see if our instrument can see those high edges. Here is a similar but a little bit more complicated application of spending more time in the area of interest than elsewhere. Finding an optimum setting can be made quicker if you are willing to abandon evenly spaced trial setting conventions. First, you must have an objective function, which is the dependent variable. This may be cost or defect rate or customer complaints or something else that is both important and quantifiable. Next, you run a trial at the two ends of the independent variable that you've obtained by bounding, as we've just discussed. Then you run a trial at the midpoint. After this initial setup of 3 trial points, you can fit a curve and perhaps refine your search near the minima if you need better answers. How this differs from a typically evenly spaced trials is that after 3 trials, you can spend effort searching only near the optimum area rather than searching elsewhere, as evenly spaced trials do. People who study instrumentation and testing and test labs are familiar with the round-robin testing methods. Here we take that same idea but make it a bit simpler. That is, to compare 2 measurement systems by simple visual assessment and to make conclusions when there are clear patterns. Lastly, I want to mention a common, but also commonly abused method. That is, to conclude that the problem cause is where you see the problem first or where you see it worst. There are potentially debilitating problems with this tool. The first is that some problems can actually move upstream from their source. An example is a truly severe wrinkling source can move upstream of where the problem roller actually is. Another example is that the source may be even further upstream yet, such as a currently invisible defect in the incoming web that may be coming from a different machine, or even a different company, or even a different country. So the safe way to state and apply this tool is that the source of the problem may be where you see it first or where you see it worst. And then again, it may not. In other words, this is a very weak indicator or clue, not necessarily a tool that can be trusted on its own. Thank you so very much for joining me in this continuation to the problem-solving process. I hope I've made the case over the last 4 modules that troubleshooting can be made easier if you are both lazy and use the tool that best fits a problem. Often, that is a street-smart tool. In the next module, we will talk about the decision-making process. Please, stay tuned. Also, please like and share.